Everybody to June's FPGA seminar, and today we've got Mark Bourgeot from Altera here in Toronto, and everybody's been anxious to hear about how Altera is doing partial reconfiguration. Mark will tell us how it's going.
There we go. Okay, great. Thanks, Paul. I'm glad to be here. So there are two goals of this presentation. One is to provide an overview of both the hardware support and the software implementation of Altera's partial reconfiguration flow. The goal is that, if you want to take on or tackle a partial reconfiguration project using Altera, you should be able to do it after this. The second is to provide a realistic view on how that partial reconfiguration flow will work. Many papers have been presented across the last 20 years, making some assumptions on architectures. Altera's implementation will be good for some and not so great for others. I want to make clear what those limitations are so that if you want to tackle a particular problem, you'll know whether it's going to work or not. So what is partial reconfiguration at the highest level? So let's consider this example system, which is basically aggregating 10 gigabit channels on the left-hand side, going through something called a muxponder, which is the aggregation step, and outputting on the right-hand side, the line side, a 100 gigabit signal, which is in this case OTN4. So for example, someone might want to change one of the components from OTN to 10 gigabit Ethernet. Suppose the company that purchased that line is out of business, or the time of day has shifted, so the demands have changed. We want to be able to do this. So partial reconfiguration is just changing the functionality of a system, in this case on an FPGA, while the remainder of the system remains operational. In this case, communication systems have very high reliability requirements, so any downtime is unacceptable. So Altera's partial reconfig strategy is to really we really focus on the software flow. We want people to enter the design intent, basically saying, I have a bunch of modules, this one is reconfigurable, and here are the different instances, and then let Quartus automate all the low-level details. We want to leverage our existing incremental design infrastructure, I'll go into more detail of that later, and our floor planning tools to make this process as easy as possible. And we want to provide an intuitive simulation flow, also including the effect of reconfiguration. So someone wants to be able to simulate their system before and after a partial reconfiguration event. We provide the ability to control this functionality either through soft logic inside the FPGA core, through I/O pins, or an external device such as a transceiver. What this effectively boils down to is we want to load the partial programming files generated by Quartus while the device is operating. We support something called configuration via protocol, for example, PCIe, so you can have a PCIe point, and that just passes the data, and this is useful for configuration speed and also minimizing the amount of I/Os required for doing the partial reconfiguration. Most importantly is that what we settled on is we want to target multimodal applications. So what that means is essentially coarse-grained reconfiguration. You're taking a relatively decent-sized chunk of your design and swapping it out with a similarly sized chunk. Very, very small reconfiguration is not what the target of this flow is, even though it is theoretically supported by our software. So at a high level, what's the sequence when someone wants to engage partial reconfiguration? So first, they need to bring up the chip with a known configuration by programming a bit stream generated by Quartus for that base image. And then someone, somewhere, makes a decision to reprogram one or more of the programmable components. Someone issues a PR request signal to the FPGA. Okay. Once it's ready, the person sends the new bit stream generated by Quartus, which is effectively the partial reconfiguration data. Once that stage is done, we receive a PR ready signal, and now the rest of the logic can interact with the reconfigured component. So in this case, you see that the 10 gigabit Ethernet entity is off chip somewhere, and after it is just replaced in that OTN system. So what will the HDL look like to facilitate this process? So this is just a sample. This is not the only way to achieve partial reconfiguration in Altera devices, but it is fairly slick in the technique we recommend. So that block, in the block diagram on the previous slide, we had a 10 gigabit Ethernet block and an OTN2 block that was being selected via PR command. So in this case, you have a module definition with a fixed set of inputs and outputs. You have a parameter that controls whether a 10 gigabit Ethernet or OTN2 is selected, and you pretty much make a case statement. So this is effectively a wrapper file around the channel that implements two different submodules, each with the effective, the capability that you want to put in there. The default statement says which one is there by default, and of course the user is free to do whatever they want in GIGI and OTN2, and anyone, the part of the chip that isn't changing interacts with reconfig channel, assuming inputs and outputs are fixed. So moving on to what the hardware looks like. So this is just a screenshot generated by Quartus of the Stratix V device floor plan. I've listed 5 different components that kind of breaks down the hardware and the rough position on the chip. This can't be used for inferring how large our die is, but it should provide a relatively accurate picture. So at the top and the bottom, we have IOs, memory interfaces, lots of clocks. The black sections in the 4 corners are not empty space in the chip. We still use them. They're mainly for various other IO functionalities, such as PLL, JTAG, the actual control circuitry that sends the bits through the rest of the chip. The green slices on the side are transceivers. Stratix V also has some hard IP blocks, various functionality. The big blue center is the core of the chip, where the labs, RAMs, and DSPs are, and those purple slices are additional PLLs and clocks. So pretty much everything can be reconfigured, but not all of the hardware components can be reconfigured in the same way. So the components in the core of the chip, that is the logic blocks, the DSP blocks, and the embedded memories, or the RAMs, are controllable by partial reconfiguration. Pretty much everything on the periphery is not. However, Altera provides IP for the transceivers and the PLLs that the user can instantiate in their design that allows dynamic reconfiguration of those capabilities. Maybe changing the latency of something, or changing the frequency of a PLL, and going into switchover mode. All of that kind of stuff is supported, but is not supported through partial reconfiguration. The IOs are probably the least configurable by the user. They do have programmable circuitry, although it's really embedded in a scan chain format, so the only way that anyway, most people interact with it is through Altera's memory interface IP, which internally sets some of those delay chains to calibrate, for example, high-speed memory interfaces. It is not, those components are not controllable by partial reconfiguration. So this is what the chip looks like from a hardware point of view. At some level, an FPGA is just merely a fixed piece of hardware with millions of 1-bit memory cells altering the functionality. This is how any design can be implemented in the FPGA. So all of those core bits, remember the labs, RAMs, and DSPs, their configuration RAM bits are directly addressable by a 2-dimensional grid, in this case frame, which represents the column, and a bit index, which represents the row. And for our largest Stratix V devices, the core contains over 10 million of these 1-bit memory cells. And by changing the CRAM values, this is the essence of how we can reconfigure individual labs, RAMs, DSPs, but also routing muxes to allow partial reconfiguration to take effect. As you can imagine, not all CRAM sequences are legal. If I have a bunch of tri-stated drivers, or like multiple drivers, if I set them all to 1, you can have a short, so we have to be careful to prevent illegal sequences, and I'll go into a little bit more about these details later. Perhaps, much to some people's dismay, that Quartus nor Altera will provide any details of how individual CRAMs map to logical functions. So being able to directly get in there and look at the, sort of a grid of what these CRAM bits are and say, oh, I want to change this to 1, this to 0, and I know exactly how that will implement the function. That will not be supported, and instead the software will be the only vehicle, Quartus will be the only vehicle to implement this coarse-grained reconfiguration that we support. So, as I said before, to accomplish a PR command, we use the handshaking technique between either the user I/O directly or through the transceiver, or from the core logic that, let's say, is feeding processing commands from an external memory. And that gets sent to that control circuitry off in the corner of the chip, and it changes that configuration RAM space as described in the previous slide. So the speed of operation, first of all, there's a small overhead to engage PR in the order of microseconds. And then the actual configuration time both depends on the size, as one would expect, but also on the orientation of the region. So in this case, because the chip is oriented in frames, tall, thin region can be configured or reconfigured more quickly than a large, fat region. So in this case, A is reconfigured 5 times faster than region B. So just as to give you a rough ballpark, this is within a factor of 2 or 3. These regions represent around 5 to 10,000 LEs, and region A can be reconfigured in 2 milliseconds, and region B can be reconfigured in 10 milliseconds. So just to put that in perspective, is that 2 milliseconds, if your circuit is running at 400 megahertz, represents 800,000 clock cycles. So any idea of changing a group of labs and instantly being able to use that new functionality, that's just not possible given the speed of configuration, which is a strong function of the hardware support that I described earlier. The way that the hardware is built pretty much dictates how fast we can reconfigure. So you say, well, what about 1 bit? What if I wanted to change 1 bit? Then that small overhead to engage PR is really the limiting factor. So it's obviously not in the order of hundreds of thousands of clock cycles, but in the order of hundreds to thousands of clock cycles to change 1 bit. So still any gains of tweaking the functionality and achieving an improvement in some sort of system just can't be done with this flow. So how do we change a CRAM bit state? So as one would expect, you can slice the chip into columns, and recall those are called a frame. So the sequence of control, when we send that PR data to the control block, what it does, it generates some instructions, 2 instructions to be exact, an AND instruction to set reconfigured bits to 0, followed by an OR instruction to set them to 1. So this is simply how one would change a bit vector in software in a 2-step process. So you'd have a masked frame so the blue, the blue bits here are the bits that we want to change. So just because we reprogram a frame, we don't necessarily want to change the state of all the bits, so we can selectively choose which bits to change. So we have that AND instruction. We have a temporary frame, okay, and then followed by the OR instruction, and then finally we get the result on the side. So Quartus takes care of all of this. It figures out what the bit stream was in the first place, what the bit stream wants to be, and automatically generates those instructions. So obviously, anyone who uses this flow does not need to get involved in generating instructions. So without going into a lot of details, since I can't, the temporary frame exists for more than a brief instant because of the way that the device is programmed. So I want to take a quick...
So, question?
Yes?
That method implies that you have to always know which programming bit stream you're coming from in order to go to a new one. You can only go from a specific one to another one.
That's a very good question. So I'm just going to repeat that in case it didn't pick up. So the question is, this method would imply that you have to know where you're coming from. So what actually happens is that the state is, the reason why that's not quite true is that the AND sets all the bits to 0 for the things that we want to change. So it doesn't matter what the bits are on the left. We know we want to clear all the bits that are involved in the region. So it's like a full mask. If I want to change this region, the following 182 bits on this frame are affected. I'm going to wipe them all, and now the OR instruction sets them to the state that they want to be. Right? So just taking a little bit of a diversion to talk about this temporary frame, that it may not be obvious, but there are some subtle electrical effects that need to be considered. So in FPGAs, NMOS-based logic is very common. It's more efficient than CMOS in the sense of size. One downside, of course, is that if you pass a logic 1 through an NMOS transistor, that you have on the output side VDD minus VT, minus the threshold voltage. So to prevent sort of this continuing degradation of signal strength, we have a weak pull-up transistor to strengthen that internal node, in this case Y, when an input signal X is VDD. So we do have you may be wondering, well, what about during chip bring-up? So we do have a global freeze signal, but of course that can't be used because this is not chip bring-up. where the whole device is being reprogrammed, only some of the device, so we have to be careful. So the AND instruction, as I was saying, causes all of the CRAN bits of this routing driver to be 0. So there's no electrical issue if X is VDD at the time at which the CRAN bit flips from a 1 to a 0, because then the weak pull-up transistor will engage and then re-strengthen the signal to Y, and we're all nice and happy because the transistor then shuts off. However, if the X is ground when the CRAN bit flips, the voltage on Y, although 0, it should be 0, it can drift because of other signals are nearby. We have crosstalk, we have coupling, capacitance, etc., and it can drift. And if it reaches a point where, first of all, any signal drifting is bad, and if it reaches a point where you can engage a crowbar current, which can have a significant power drain. Now, if only one routing mux fell into this condition, then that's typically not a problem. Obviously, it's not going to fry the chip. But if you're reprogramming quite a large region, depending on the sequence of AND and OR instructions, you can have 10,000 of these routing muxes fall into this state. And if they all draw a very large amount of current, that can significantly negatively impact the device and also fry it at some level. So we need to be careful of this. And I'll be discussing later how the software automatically deals with this case. So at a high level, this is what Quartus needs to do in order to use this hardware. The user needs to provide design files, obviously HDL, and a bunch of project information that basically says, I want this piece, this block, to be reconfigurable. Okay. It runs Quartus, the user runs Quartus, and in the output you have multiple reports fitting timing, power, and also multiple bitstream files. So one for the full chip, which represents the image that is going to be initially loaded into the device, and then one per persona. And I'll define what a persona is next. Effectively, that is a region, an individual instance of a reconfigurable component. So what this effectively means is that we're going to need to run Quartus multiple times in order to produce these multiple bit streams, because the number of bit streams is a function of how many partial reconfiguration instances you have in the design. But first, I'm going to give a quick background on our incremental compilation or incremental design flow. So we provide the users the ability to specify partitions or groups of hierarchies in the design. So in this case, I may choose to create 3 partitions, one for the channel 1, one for channel 2, and one which represents a grouping of the mux ponder and OTN4. Seems pretty reasonable since mux ponder and OTN4, if you recall from the earlier slides, they're not changing, but the channels are. So we want to, anything that is actually changing, you want to put in its own partition. The way that Quartus handles incremental compile is that we provide the ability to independently recompile any partition. So what this means is that CAD optimizations across partitions are prevented, because that would clearly violate the ability to independently recompile them. And also, when you recompile a partition, all the other partitions are imported, and that means that the synthesis, placement, and routing is preserved exactly. And this is important in order to ensure that we can generate the union or all the bit streams and make sure that they represent a consistent set of information that can be programmed into the device through the PR commands. As a side note, this incremental compile flow still supports multiple processors, so it's, you can get the fastest possible compile. So incremental compile is much faster than a regular compile. So in this case, you have this partition has 2 implementations, and then logically, you specify the design like this, and you can plug and play at a partition level. This gets us, yes?
Do you have to have floor plan information in advance before you perform this?
That's a good question. So the answer is yes for the reconfigurable components and no for everything else. So for design, for this particular design, the entire design hierarchy would look something like this. So the mux ponder and OTN is called a static partition because it's going to exist in the design at all times. And you have 2 partial reconfiguration partitions, each with 2 instances, or also known as personas. So in this case, just to be absolutely clear, because the rest of the presentation kind of depends on it. The above design hierarchy has 4 personas, 2 belonging to C1 or PR partition 1, and 2 belonging to PR partition 2. And as you just asked, the PR partitions must be assigned to the fixed regions of the chip, because otherwise it would be impractical to talk from the portions of the chip that are always there to the portions of the chip that are just coming online. So what is a project? Like normally when you create a project in Quartus, it's pretty simple, I guess. You just say you have a bunch of settings and a bunch of design files, and you hit play, and then you get some reports. Partial reconfiguration project is a little more complicated. There are 3 different types of revisions. Now, a revision is a set of input files for a single compilation. This means you can change the parameters, such as the parameter controlling the instantiation of what's in the HDL file. You could change the timing constraints, and you could change very detailed things such as the fitter effort level. So suppose you have 2 personas where one is easy to fit and one is difficult to fit. You can actually control that on the difficult to fit, you give it more of an effort level, and that minimizes your overall compile time. So there are 3 types of revisions. There's the base revision, and then that compilation, its purpose is to compile the content that always exists on the chip. And this is also known as a static compilation. Then you have a group of reconfigurable revisions, and these compilations, plural, are responsible for managing the content that can be programmed via PR commands. And then finally, you have something called aggregate revisions that are user-defined groupings of reconfigurable revisions. So why would we need aggregates? So consider if I have a design with 10 PR partitions, and each partition has 6 different personas. I actually really have a million possible combinations of what the device may look like at any given time. Quartus is obviously not compiling a million combinations. However, we provide the ability for you to select any of those million, by defining, say, hey, I want this one, this one, this one, this one, this one, and we'll group them together for you and run that compilation. So there's no limit to the number of regions or number of persona per PR region. At some point, the output is a bit stream. If you do have lots and lots, it will take longer and also require more off-chip memory to be able to load them, but the software doesn't impose any limits. So this is sort of again, a walkthrough of a pictorial version of what I just said. So the first compile is compiling the logic that will be there all the time. So in this case, the user has defined the floor plan for PR1, which is non-rectangular, or a union of 2 rectangles. PR2, and then the rest of the chip is where the static logic is placed. So, and the user can choose what they want to appear in the base compilation for the partial reconfiguration. They can set it to empty to minimize the speed of the compile. They can specify it with the initial content that they want programmed onto the device, or you can specify the hardest to route persona, because there is some interaction in the software of how the static logic is compiled depending on the content of the other chip. And that will become more apparent later. So the output of this compile is a bitstream file, which of course is the one going to be loaded into the chip initially, and also some internal databases that will be used to compile the later revisions, that is the reconfigurable revisions. So there are 4 reconfigurable revisions for the project that I just mentioned, and there's a pictorial view on the top right of the chip. So each of these compilations imports, using the incremental compile framework, the placement routing of that base revision, in this case all of that static logic. So Quartus can now compile all of these persona in parallel, and this is process level parallelism, not thread level parallelism. And as an optimization, one can combine the persona of different regions together. So for example, I can compile these 4 individual personas in 2 compilations. For example, the first one, I could put persona 1 of PR1 and persona 1 of PR2 in one compile, and persona 2 of PR1 and persona 2 of PR2 in the second compile. So I really need to do 3 compiles total, but the output will be 5 bit streams. The full bit stream for the static compile, and the 4 partial bit streams for the individual compiles over here. That's of course just an option. You could choose to invoke 4-level, or to minimize the latency, You don't actually compile them together. This will require more processes, but if you have a huge farm, you can really minimize the overall latency. That's something we really thought about when designing the overall flow. For very large designs, they can take hours to compile, as many of you know, and now we're talking about layering multiple compiles, and to be able to minimize the end-to-end latency is a very important objective.
Sorry, when you say compile them together, are you allowing optimizations across the two PR boundaries to occur?
That's a good question. Are there optimizations across the PR boundaries? So not synthesis or placement. So synthesis is obviously, it leverages the incremental compile framework, but once both PR personas are alive, there is some sharing of routing resources, and I'll talk about that later in the presentation. And just as a I guess corollary is that the number of compiles is 1 plus the maximum number of persona across all regions. So you probably don't want to create something with 20 personas of one PR region and then 2 personas of another PR region, although some designs may require that. And finally, there's the class of revisions called the aggregate revisions, and this is where you compile user-defined groups together. As I said, this step is completely optional. The first 2 classes of revisions produce all the bit streams that one would need to program the chip and accomplish any sequence of PR commands at any given point in time. However, this step is useful for generating a complete bit stream without requiring PR commands for the set of logic that you want to put in there. So let's say you want to see persona 1 of PR1 and persona 2 of PR2, so that compile wasn't actually performed in the reconfigurable stage, but say I want to see that chip. It generates a complete bit stream which can be programmed, and you can now test it on the board, and also run all of the auxiliary functionality of Quartus, such as timing analysis, simulation, visualization, and chip planner. So this is just a useful step. So we have a dedicated GUI inside of Quartus to navigate all of the contents of this partial reconfiguration project, or you could say collection of projects. From this GUI, you can directly launch the regular Quartus GUI for a specific revision. You can easily create new revisions. You can sort of do a compile all via a single click, and this is a sort of an intelligent recompile, so if you change the base, it knows that it needs to recompile other revisions, and you can obtain a summary of all the compiles since your system is not really complete unless all of the compilations meet your timing constraints. So this is just a rough flow chart of what we're recommending that a person, what they're signing up for effectively when they want to do a partial reconfiguration design. And I just want to highlight 3 of those rectangles that are obviously colored in red. So the first one, and probably most important, is that before you do anything, you must plan your system for partial reconfiguration. People that just even try to do incremental compilation, it's something that with floor planning, it's very difficult to do after the fact. And partial reconfiguration, it really requires, because of floor planning, figuring out which modules need to be swapped out and structuring both the HDL and the resources of the chip around the fact that you're going to be doing partial reconfiguration. You assign the partitions to logic lock regions, so those are just non-rectangular regions in the chip. So we do provide a way of doing this automatically. We have something to automatically determine what's a good region size. However, depending on the amount of connectivity, one may want to really think about what those regions are. So that you might want to have a very sort of a finger shape if there's a lot of connectivity between the PR regions, and our automated way of doing that will not take into account advanced requirements such as connectivity. So it's for something to think about up front. You really want to have a good idea of what your floor plan will be. And also, is timing met? So that, if the answer is no, that's a very large loop. So that's I think that's a problem for anyone wanting to take this down this road, which is why it's important to really be modular and make sure that each design is able to meet time, or each persona is able to meet timing independently, such that when you do the entire system, you don't want to come up with a situation, well, I have to change what my data path looks like in the base revision, because that will trigger a recompilation of everything, and realistically, that design cycle will be more expensive than just doing one compile at a time. So it's primarily the multiple compilation aspect that introduces new software challenges. I'm going to talk about 4 specific issues that we've had to face that may have become apparent to you. So first of all, we have to handle how I/O works in PR partitions. Basically, the part in the static region must stay in the same spot across all compiles, and that there must be some sort of fixed point, whether it be a wire or a LUT, that can be counted on, such that when we change the chip's contents from one persona to another, the design automatically works. Our FPGAs have a fixed set of routing resources. We need to partition them across all the compiles to balance the desire for optimizing one compile versus the fact that multiple different units need to fit together. So an obvious restriction is that different PR partitions cannot use the same routing resource because the CAD tool must assume that any persona of partition 1 can be loaded with any persona of partition 2. However, different persona in the same PR region can use the same routing wire, and we need to take advantage of that, or else the design would pretty much be unroutable. Certain shared FPGA resources, such as the clock networks, are an especially difficult problem, and I'll go into more detail on that later. And finally, we provide the ability to do time enclosure of cross-partition paths. So suppose you have a register transfer where the source register is in one PR partition and the destination register is in another PR partition. That represents a challenging time enclosure problem because there's no guarantee that the CAD tool will actually see the full path in any given compile. So, yes?
So speaking of the routing resource sharing, right? So I'm a little bit worried that when doing initial floor planning, because of the rectangular nature, you create blockage. So is it possible to create reserve some feed-through kind of resources?
So yeah, I'm going to be talking about that shortly. What happens is that, so the question is that when doing a PR design, worrying about blockage. So what happens is that even though you define a region on the chip, it doesn't actually represent a hard wall for the static region. And I'll be showing about how routers work later. So just recall this electrical problem with the ground inputs. So there's really 2 main options here. One, the user can guarantee that the inputs will be VDD. The inputs to a PR partition will be VDD when partial reconfiguration is enabled or engaged. And option 2 is that just let Quartus solve the problem automatically. So I'm going to describe the second option because the option 1 is far less interesting. So what we do is for every PR partition, we reserve 1 LUT for ground. Its only function is to generate the ground signal. And for each input signal going into a PR partition, we add an OR gate outside that PR partition, so it's not going to be reprogrammed, and connect the ground LUT to the other input of the OR gate. And then we connect the OR gate's output to a 1 input anchor LUT inside the PR partition. And that anchor LUT will be, well, it's just a regular LUT, but it's called an anchor LUT. That LUT's position will be constant across all compiles. Okay? This connectivity is always inserted in that first base revision of the static compile. And using incremental compile, all subsequent compiles will import this logic, which includes the ground LUT, the ORs, and the anchor 1 LUTs. And then that's the guarantee, because our incremental compile flow for 100% preserves placement and routing through compilations. This is what guarantees that the PR input process can work. Now you're maybe wondering, well, what about the ground LUT? So during the PR operation, the output of that block goes to a 1, and then that's what causes the OR gate to obviously output a high signal, and that phase occurs before the AND instructions are launched. So it's a little bit of low-level details, but I just wanted to provide a complete view there as to why the OR gate and ground LUT works. It's because during PR, it actually becomes VCC. So on the output side, a similar technique is used, but it's much simpler. So we create an anchor 1 LUT inside the PR partition and connect that output logic to the static region according to whatever the HDL files say. And similarly, the incremental compile process ensures that 1 LUT will be in the same spot from compile to compile to compile. So what this means is a corollary, if you want to just have a pass-through, you are going to go through 2 LUTs inside every PR partition. So, yes?
Sorry, are these anchor LUTs placed in a way that you can guarantee that that's the last LUT to change when you're reconfiguring a region?
That's
so that
the
way it kind of acts as the signal to say this region is now been fully reconfigured.
So that's a good question. So does this anchor LUT act as the last one to be reconfigured? Is that the question?
Yeah.
So the way that a user knows that the design is ready or the PR partition is ready is that there's a signal coming from that control block saying this is ready. So it's expected that that signal is wired up to the rest of the circuitry to declare that it's done. One cannot assume that the order of the LUTs is in a particular order.
So internal to the PR region, you can't generate a self-time signal that says I'm now fully active.
That's correct. So this is obviously a question of one of the biggest decisions to make when doing software support is whether to do the anchor at 1 LUTs. And pretty much right off the bat, there's some obvious pros and cons that exist, and I just wanted to run through them. So first of all, the use of an anchor LUT increases the routing flexibility on inputs and outputs. Both FPGA's architectures and the CAD tools aren't designed to route from and to specific wires, which would be the alternative if you didn't use an anchor LUT. Also, by providing an anchor LUT, you actually have a well-defined problem for each compiler. The base revision routes to the LUT, okay, or from the LUT, and then the persona compilations route from the other side of that LUT to wherever the rest of the logic is. Otherwise, it's a difficult problem since you really have this OR gate and multiple personas, and then who really decides how that path is chosen? There are ways to do it, but it makes the problem more complicated. Additionally, one thing to note is that we will allow the inputs to branch from the sequence of routing wires chosen on that base revision from the OR gate to the 1 LUT to allow direct connection and then bypass if needed for time. So obviously creating a 1 LUT reduces the number of usable LUTs in the PR region. If you have a region with 1,000 LUTs and you want 500 signals coming in, that represents a 50% overhead, so that's a big downside. And as I already mentioned, it increases the latency of signals entering the region. So going back to the question about route throughs is that, like, what about, so I have a floor plan, perhaps it's pretty complicated, how are we going to deal with this? So our hardware supports the reconfiguration of individual routing muxes. This enables route through of the PR regions automatically. And this simplifies many floor planning restrictions. So what happens is that OTN4 base compile, it wants to talk to the transceivers, it goes ahead and uses whatever routing resources it wants to, okay? And then the persona compilations, which import that placement and routing, know that those individual tracks were used in the original compile and therefore can't be used. So as you can see, this allows very complicated floor plans and provided, so you still need to manage the overall connectivity and the amount of signals going through, but it's, you're not going to significantly increase through detours.
So that means persona always depends on the base compilation on the static version.
That's correct. So one can consider perhaps a more complicated example of what if I want to have an output of PR region 1, which has many personas, talking to an input of PR region 3, which also has many personas. You don't know what you're coming from and you don't know what you're going to, but you know you want to hook them up together. So our design decisions that I just described actually makes this completely trivial to support. Because we insert the anchor LUTs and OR gates on that first compile, okay, we are able to reserve those routing wires to complete the necessary connections to achieve the inter-region communication. And then when we import just that small little subset, which looks like just be a floating set of nodes, into all the persona compilations, those resources are disallowed, and then whatever you put on either side just gets hooked up together and it just all works.
Isn't there an order of compilation issue that shows up then? Because when you do PR2, you have to kind of know the PR1 and PR3 want to talk.
No, because all the blue logic here, okay, is compiled before any personas are even being done, right? And using incremental compile, right? This is part of the base revision. We import that placement and routing. And so whether you do PR1, PR2, PR3, in fact, all in parallel, right? They know, all of them know that here are the wires used by that first compile, and they can complete the connection. One thing I should note here is that it is a minor issue, is that OR gate needs to be in the space of the chip that is not occupied by any other PR region. So if you have these abutting walls, you may get a very unfortunate placement of these OR gates, but that problem is easily rectified by reserving sort of a buffer region around PR regions. So global networks are global, we provide many different layers of global networks in our devices. I don't want to go through all of them now, I just want to provide one as an example. So one type, and probably the most common, we have 16 chip-wide networks that are a balanced H tree that can reach every block. These are for distributing clocks, asynchronous clears, and other extremely high fan-out signals. So our design structure, or device structure, says that only 6 of those unique clocks can drive every row clock region. And this is a region of 12 by 1 blocks on the chip. And our compiler takes this into account all the time. This has been true for quite a while. And normally what we do is so if a region is an intense desire for clocks, we just make sure that we don't put logic that, it's just a placement constraint. Sorry about that. So, however, this impacts PR in a much more subtle way, and that such to the point that all PR designs and PR designers should consider clocking regions. So basically, if you match the region side to some sort of quantization of these clock region boundaries, you actually have a much easier problem. However, Quartus supports any PR region. It just reduces the amount of routing flexibility you have for the global networks, and this is going to be described right on the next slide. So one thing that we assume right now is that the place and route engine basically is conservative for clocks entering PR regions, and it assumes that every clock can be feeding every location in a PR region. So obviously this can be improved upon, but it's a challenging problem, because if I have 10 different personas and 3 different clocks, it's hard to know how many different, exactly how to do that clock assignment problem. So here's a more detailed picture that talks about sharing wires between regions. So this just is a clock buffer on the edge of the chip, and these black lines represent the available wires that exist on the clock network. So suppose I have 2 registers in the static logic, so a base compile. So on the first compile, we're going to use this blue sequence of wires to reach those destinations, and those wires are going to be alive as soon as you program the chip. So they're in the base revision bit stream. So region 2, that one has been designed well, and that there's no overlapping nature of the PR region. So these wires represent optional, they can be optionally used by a persona bit stream for that region. Some personas may use them all, some personas may use none. Definitely the personas that will reuse the blue wires, because those will be those will exist, and you can branch off of them, but sometimes the green will be using. So the purple wires, again, those don't have any overlap, and they are optionally used by a given persona bit stream in region 1. But the key thing to note at this point in the slide is that there's no connection from the blue to the purple. And the reason for this is that this sequence, or this portion of the clock tree, connects both to PR region 1 and PR region 2. So it's a little bit complicated, but the CAD tool cannot assume that any particular persona exists at any given point in time. So therefore, those orange wires actually need to be in the base revision's bit stream, even though the base revision doesn't use them at all. Because based on the ordering of the PR commands, you can't assume that let's say PR region 2 doesn't own those wires, so you need to ensure that they exist all the time. Perhaps a complex example, but is one of the things that Quartus handles automatically, and I guess a warning to say why sharing global resources between regions is somewhat dangerous. I only have a few more slides, so talking about time enclosure. So the simple way to do time enclosure is that you have registers at all PR partition boundaries, and this ensures that the fitter will route all these intra-region connections for minimum delay. So in this case, the anchor LUT to register 1 and register 2 to the anchor LUT will be routed for minimum delay, and this requires that the OR gate being placed before register 2, and that optimization can be performed, assuming there's no clock enabled. And then now when you consider your persona logic, you have the compiler sees the register path, since the reg1, reg2 are always part of the static region and imported into the persona compile. And since every path has at least one degree of freedom, that is one connection which can be optimized, we can either route it as fast as possible or add more delay in the case that there's a complicated hold timing requirement between the two registers. In a more complicated case, the user needs to explicitly manage the clock period. So from this picture, which is pretty much the same as the previous slide, you divide it into 3 segments. One from the source register to the boundary of the first PR partition, one from the boundary of the PR partition, one PR partition to the boundary of the other PR partition, and one from the boundary of the last PR partition to the destination reg. And you use SDC constraints to manage that transfer. Again, no given compile will see the end-to-end path, so you need to budget it to ensure that the end-to-end one is met. Using an aggregate revision, you can actually bring in the full combination and guarantee that it will work, but the Quartus will say that if you violated your budget, you will have failed timing. But that actually doesn't represent a complete failure if every combination of the aggregates will pass. This is probably not able to be seen here, so you have a bunch at the top on how the clock period is divided into 3 phases. You create 3 clocks, 1 representing the whole clock and 2 representing sort of virtual clocks from the boundary of each PR partition downstream and the boundary of each PR partition upstream. And then you assign a bunch of latencies to the clock signals that are provided by Quartus at the original compile. I'm going to skip the rest of this. Again, the main thing here is that you can say, okay, the output delay is 0.6 nanoseconds, the middle delay is 2.1 nanoseconds, the last delay is 0.6 nanoseconds. That's how you can achieve a 300 megahertz clock. Okay, so lastly, just 3 ideas of where we want to go with this. The first is translatable bit streams. So consider the following system that looks, again, very similar to what we've seen before. 10 different PR regions, each region having 2 personas. However, if you look at there's only 2 unique personas, that is, based on, if you just look at the HDL, for the entire design. Now, users would love to be able to run, to only have 2 partial bit streams, and then just take that and translate them to other parts of the chip. Right now, our flow runs 20. So this is difficult. So our architectures aren't quite built for this, and also the CAD tool support for this is very difficult. Nevertheless, we are working on this because a lot of customers have expressed significant interest, and this will allow to build much more complicated systems in a manageable amount of time.
What do you mean by translatable?
So the output
Location?
translation in space.
Okay.
Right? So yeah, so if you think of the chip as a 2D floor plan, I have a 10 by 10 region, I'm just going to shift it in different positions. And that the reason why that's not trivially supportable is that our routing architecture is not homogeneous to the point where you can do that. I can take a place and route, and if I try to move it over, it'll just fail because those wires don't exist. So next, there's an open question of how we partition those resources among the compiles. So enforcing hard boundaries of the routing resources in PR regions may significantly increase fitting difficulty. So one way to go around that is to make the regions larger, but that reduces the efficiency of the chip. So this approach guarantees legality at the expense of optimization quality. So we actually have 2 approaches. One, which will be supported in the next version of Quartus. I should have mentioned that at the beginning. So all of this will be available in Quartus 2 11.1 for the Stratix V device family. And so option 1 is I can partition unused resources between PR regions. So I have my base revision. That has its choice to use whatever routing resources it wants. Yes, we have cost functions to try to prevent it from using the PR routing resources because that's expensive. But it's not going to use 100% of the routing resources in the chip. So we can do some sort of painting algorithm based on Manhattan distance that basically says, okay, in all subsequent compiles, every persona of PR1 not only can use the routing that is directly within that region, but it can also use all the additional routing. So this makes the fitting easier at the expense of making that when you change base, there's a greater chance that that's going to impact, that you're going to have a collision and now going to recompile the entire system. Also, it will actually make the configuration time a little larger since the region that you need to reprogram increases. Secondly, probably more complicated, is that you can actually allow regions to use any resource, use any routing resource that it wants, and create an outer loop to iteratively resolve congestion using a cost-based system. So this is similar to negotiated congestion, but at a macro scale. And instead of BPR router, which I think has tens or hundreds of iterations, we probably only do 2 or 3. So this has again, increased latency of the overall compile, and it can significantly increase cost of changing the base. But if you have a difficult PR problem and you're fairly sure you don't need to change it, that idea will allow maximum optimization potential. And the last thing, although we don't quite know how to do this, is to minimize the overhead. So our current software implementation approach works very well for multimodal applications. You know, you're taking thousands of LUTs, moving them out, replacing them by thousands of other LUTs, because the overhead is much less than the PR region size. However, you can conceive of applications that wants to create hundreds of very small regions and perhaps have lots of input signals and very complicated systems, and our current software approach doesn't prohibit this kind of design style. We haven't seen a lot of market demand for that kind of application yet, but nevertheless, we are always working on trying to minimize the overhead and allowing people that want to do multimodal applications to do what they need to do efficiently, and also people that want to build these advanced systems with hundreds of regions to be able to do that efficiently as well. So what have I shown here? Altera devices have flexible hardware support for partial reconfiguration. We can reconfigure labs, RAMs, and individual routing muxes, which allows route truths to be handled easily. We have a well-defined flow for implementing multimodal applications using PR. So it's intuitive design entry, simulation, and also a wrapper GUI that allows quick access to any individual combination of personas. And the user can also manage complex timing situations between PR regions, provided they take an initial care in doing this. And I've also shown that Quartus automatically handles many of the implementation details efficiently and effectively, including the OR gate insertion, so the route throughs, and also some advanced cases of clock resource sharing when they cross multiple PR regions. So that's all I have. Thank you very much.
Questions?
Yes?
So I'm talking about the global clock sharing. So suppose in the initial design, the user had, say, 2 different personas, and there is no sharing of global resources. Then the persona is not going to have those that sharing infrastructure. Later on, if that designer has to add a 3rd persona after the system is deployed, do they then have to like rechange the 1st and 2nd persona?
So it's a good question. So it was about the addition of a persona impacting clock region sharing. So it's really more of a structural problem based on how the PR regions are defined. Right? I can just look, like, without even talking about personas, if I know that the rectangles that if you have for a fixed logic lock region of 2 PR partitions cause an intersection of any given region, I know right at the base revision that I need to put those clocking resources in that base revision bit stream. So if you change the pretty much almost guaranteed, right? If you add a new PR region, your base is going to need to change. But if you add a new persona, that doesn't change the decision whether clock regions will have some new form of advanced sharing.
Is it possible to disable the route repeatability? The reason I ask is because, let's say, so you were talking about lots of small PR regions, and I know one of the researchers here, I don't see him here right now, but he was always asking designers folks, what happens if I have the same design over and over again in different regions of the chip? And the answer is the same design, so you have to recompile it every single time. Here, there seems to be an additional difficulty that if you're doing a route across that region, then that becomes even more specific. Whereas in Xilinx, it's generally just a timing problem. Here, it's also a routing problem as well.
Okay, that's a good point. So the question is, do you have the ability to disable route throughs?
Yeah,
So
across PR regions.
Across PR regions. So the answer is not easily. So we do usually have a routing constraint file format. That's something that if we see desire to add, and as you mentioned, it's probably targeting the more fine-grained reconfigurable applications rather than the multimodal ones, then that's definitely something that we believe we can add. Yes?
I was just wondering if you've thought of doing more optimization in that time enclosure method where you were allocating portions of the clock period among 3 regions. You know, say one region didn't use up all its slack. Have you thought of putting a loop around that and maybe making life easier for the other regions or anything like that?
Okay, so the question was, is that any more comment on optimization when there's a complicated time enclosure problem? So the answer is no. So again, this is 11.1, which hasn't been released yet. I think it'll be released sometime in October. This is our first release of the software, so we had, at the current time, the answer is no. Right? That may significantly increase the latency. And again, with the STC file, the user can pretty much control whatever they want, right? Probably a good design technique is to over-constrain all 3 regions. I expect a common case is that most register paths will not cross PR regions, but rather, people will likely be registering the boundaries. But maybe not. Yes?
Are there any easy ways to generate a reset internal to the PR region, or does it always have to be reset externally? So when you finish reconfiguring a PR region in circuit, generally the recommendation is to reset it externally so that you know it's coming out of last state, because you can't rely on global reset nets or anything like that. But in some designs, it's desirable just to have the block unit itself without any external interaction. Is that possible? It's sort of the question I was asking about anchor LUTs earlier. Whether you can guarantee that this signal or this regionally is alive now and is fully configured.
So I'm not sure I fully understand the question, because even if you guarantee the anchor LUTs, that doesn't say anything about the internal state.
If the anchor LUT output is being used to keep the device in reset, or to keep the PR logic in reset. So let's say I'm initiating PR external to the chip with a scan chain or whatnot, or I don't know if there's a parallel increase or something like that. Once that's done, I don't want to have to figure out a way to insert an I/O or something like that to let the core FPGA logic or the static region FPGA logic have to inform the PR logic. Okay, now you're free to go. It's ideal if you could just do it itself.
So, unfortunately, I don't have the answer to that question. So I believe a lot of the state, right, such as because it's different than device bring up, where you have different power rails coming up. Right here, all the power rails are a lot. So, for example, let's say the contents of, let's say, an embedded RAM, that will be part of that partial bit stream. So it will be, in fact, well defined. Is that every signal will be, every register will be in its original state, and that. So I don't believe I think you can do it without having an additional reset. Although, of course, designers that want to fire that extra reset off. I haven't thought much about the case of the PR region itself generating a reset signal to other PR regions. So I can't answer that question. Yes?
I was wondering if you could comment on the benefits of grouping PR regions together. Where, like, you said that the user, there's a million different potential combinations, but the user can specify a few that they want to be compiled together. Then you also commented on how there was limited optimizations that happen between two. So if you wanted to group two personas together, there's limited optimization that happens across persona even in that case.
So that's a good question. So the question was about grouping personas together in the aggregate compile, and how that actually affects the optimization of the reconfigurable revisions. Is that correct?
Yeah.
Okay. So it's a good question. So the creating aggregates, again, is completely optional. It's really more of a post-processing step that pieces things together to allow users to have direct control of what they want to see, and sometimes particular combinations, like in the case I said, 1 million theoretical combinations, but then there may only be 10 practical combinations that gets more direct access to timing reports and visualization and even a bit stream. As for the compilation of the reconfigurable revisions, there really isn't much optimization potential, right? It's like you have routing resources that, and let me just go back a couple slides here. So this painting algorithm, right? So I had two PR regions compile at the same time, so two different PR personas. The entire universe of routing resources that exist on the chip are partitioned between you. So provably, whether you compile one independently or both together, you will actually not get a different result.
Can you not create a separate region that encompasses all those personas? And what's stopping you from doing that?
A region that, so like a super PR region?
Yeah.
So there's nothing that stops that. However, what you define as the PR regions and the personas, that essentially defines what the chip can PR, right? So you want to combine two together into one PR region, that's great, right? Full optimization, complicated resource sharing, synthesis placement, everything that's going to be optimized. But you're not going to be able to say, oh, now bring one in and not the other, because all of those steps of adding the anchor LUTs and really defining boundaries and getting those partial bit streams, it's not about combining and then the tool can just separate it out at will. Hopefully that answers your question a little bit. Yes?
So this is somewhat of an unusual question, but suppose the user had a situation where they knew that their design in certain scenarios can operate very slowly and very low power. Can they use partial reconfig to just put all the labs to like low power mode? Does the user have control that?
That's a great question. So can PR be used to lower power by putting it into a low power state? You can actually do better than that by one of the personas that is implicitly created is called sort of the empty persona, which is just those anchor LUTs and nothing else. So if you really don't want to use that block functionality, you can program in through a PR sequence that empty bit stream, and then you have no labs. Of course, if you wanted to have a lower power implementation of the same function but slower, again, that's another option. So you can in fact implement the exact same functionality, but just with a different power performance trade-off. Yes?
So it seems to me that there are advantages in terms of usage, design flow point of independent partial reconfiguration. So one of the questions that I have is could you make this design flow work for low-end devices or other devices or legacy devices that does not support partial reconfiguration? But for development, I think I see advantages of having developing a platform using the base reconfiguration and also other IPs or whatever using partial reconfiguration. Is it easy to make it work?
So that's an interesting idea. The question is can I use this framework to perhaps for IP or legacy devices? The answer is, so incremental compilation is supported for all Quartus families. So a lot of this notion of preserving state and importing placement and routing exists. The ability to insert anchor LUTs doesn't exist right now. So I see nothing that would preclude the software flow from supporting it. But obviously, for a device that physically doesn't support it in hardware, you wouldn't be able to generate commands. But yeah, I actually see nothing that precludes the software flow.
You only need to basically compose several bit streams into one final stream.
That might be possible.
Well, I have actually a second question. Is that it seems to me that the initial floor planning is very important because it seems to dictate a lot of performance later on. So, is it true that your current user interface is running a view-based approach? Is there any support for programming support, like a particular script that the user could create their own floor plan?
Yes. So all of our commands, right? There's a tickle package for partial reconfiguration and pretty much any incremental compilation. All of what I described here about setting up the project and compiling the project and the different revisions can be completely programmatic.
But is it documented?
It will be.
All right, any other questions? Okay, so let's thank the speaker. Thanks for our great talk, Mark. And so if you haven't known, so Von Betz, who used to sort of pay for the pizza for Altera. We'll be joining U of T at July 1, and I'd like to introduce Paul Ventus, who former graduate from here, who's taken over Lon's position, and he's paid for the pizza for today.